All right, today we're talking about something that honestly sounds like it's pulled straight from a sci-fi movie. We're looking at an AI system that literally teaches itself how to get smarter, evolving all on its own to tackle some really complex coding problems. It's called the Huxley-Gödel Machine, and believe me, it's a completely new way of thinking about AI.
So let's just start with the big question, right? The one that keeps AI researchers up at night. What if a machine could not only write code, but could rewrite its own code to become a better version of itself, potentially surpassing the very people who built it in the first place? This isn't just some far-off idea. It's the real question driving this entire field of research. But here's the thing. Creating an AI that can actually improve itself is a massive puzzle. The most obvious path, just find the AI that scores highest on a test and have it make the next generation, well, that turns out to be a really bad idea. Let's break down why the best isn't always, well, the best.
I mean, look at this. This chart just lays out the problem perfectly. On the left, you've got an AI agent that aces its tests. You'd think that's the one to bet on, right? But pretty soon, its descendants just hit a wall. They completely stop improving. Meanwhile, look at the agent on the right. It seems kind of weaker at first, but it gives rise to a whole family line that achieves incredible long-term success. And there's actually a name for this whole problem: the Metaproductivity-Performance Mismatch. It's a bit of a mouthful, but it's just a fancy way of saying that how well an AI does on a test today is a terrible predictor of its potential to get better tomorrow. A high score doesn't mean it has any clue how to create a smarter version of itself. Okay, so if just picking the top scorer is the wrong move, where do we find the answer? Well, the solution, and this is just brilliant, comes from borrowing an idea from evolutionary biology. It turns out it's not about the individual, it's about the entire family tree. And that's where this key term comes in: a clade. In biology, a clade is just an ancestor and all of its descendants. Seriously, just think of it like one whole branch on a family tree. It's about looking at the entire lineage, not just one person. And this concept, it's the secret sauce. And this is the big mental shift. The crucial insight is to stop testing just one AI agent, and instead to evaluate the collective success of its entire family line, all of its descendants. That gives you a much better signal of its true potential. So, with that idea in mind, we can finally introduce the hero of our story, the Huxley-Gödel Machine, or HGM for short. It's an algorithm built from the ground up to solve this exact problem by taking that smarter, lineage-based approach to evolving AI. See, HGM couldn't care less about one agent's individual test score. Instead, it uses this really clever metric called Clade Metaproductivity, or CMP. And all this does is measure the combined success of an agent's entire clade, its whole family tree of future versions. It's a way to actually quantify that long-term potential. So how does it actually work? Well, the process is really elegant. HGM takes a look at an AI agent, then it examines all of its descendants, its whole family line. It calculates the CMP for that entire group, and then, and this is the key, it picks the original agent whose family showed the most promise and prioritizes it for the next round of evolution. And you know what's really cool about this is the theory behind it. The HGM is basically a real-world practical version of something called the Gödel machine, which is this legendary, theoretically perfect self-improving system that's, basically impossible to actually build. HGM takes that pie-in-the-sky idea and makes it work. All right, so the theory is cool and all, but does it actually work? Let's get to the results, because this is where it gets really mind-blowing. This isn't just some idea on a whiteboard. HGM is out there achieving stunning human-level performance. Just look at the numbers on this really tough software engineering benchmark called SWE-bench. The proof is right there in the pudding. The agent discovered by HGM hit nearly 57% accuracy, which just blows past the agents found by other methods. It's not just a tiny bit better, it's a significant leap forward. And get this, it's not just about the quality of the agents it finds, it's about the speed. HGCM found these superior agents almost 2.5 times faster than the next best method. So it's more effective and it's way more efficient. That is a huge deal when you think about the time and money it takes to train these things. And this right here is the headline. This is the big one. When you take the agent that HGM discovered and pair it with a powerful next-generation model, it scores 57% on this benchmark. That is right on par with the absolute best result from a human-engineered agent. Let that sink in. An AI has evolved another AI to perform at the same level as top human experts. So let's zoom out. What does this all really mean? We're not just talking about a better algorithm. We're talking about a fundamental shift, a whole new paradigm for how we approach building artificial intelligence. All right, so let's boil this all down. What are the key takeaways? First, just chasing short-term benchmark scores is a trap. It's a dead end. Second, the winning strategy is to look at an AI's entire family tree. It's Clade. And third, the Huxley-Gödel machine puts that exact principle into practice, and the results are human-level performance. This really moves us away from just gaming a test and towards actually cultivating real long-term potential. And all of that leaves us with one final, massive question. We now have a practical way for an AI to design a better version of itself. Once that feedback loop of self-improvement really truly kicks into high gear, what happens next? I mean, really think about that. That's a question we're all going to be watching unfold.